Move on now to our next talk, custom road network contraction for routing. Laure-Hélène Bruneton is with us. Hello, good
Hello, can you hear me?
evening. Yes, we can hear you.
Yeah, perfect.
Take control of the screen if you can. I think Ben by now will have relinquished his share, and you should be able to take over the screen share, and we can see your talk there. I'm gonna ask you to go ahead, and we'll ask you questions when you're done.
Okay, so I can't see myself anymore, but you are seeing my screen?
We are seeing your screen.
Okay, perfect. So first of all, thanks for the previous talks. It was really interesting. Mine will be a bit more project-oriented. But first, let me introduce myself. I'm Laure-Hélène Bruneton. I work for CampToCamp, and I'm going to present some job we did on custom road network projection for one of our projects, which is called Nexus. So we'll start the presentation. Yeah. A bit about my company. So CampToCamp, we are based in France, Germany, and Switzerland. We are working for more than 20 years in geospatial solutions. And we are one of the major players in open source in Europe. We are integrators, editors, contributors in all main open source geospatial projects like QGIS, OpenLayers. We try to be involved in all the aspects of geospatial. Then a bit about myself. I've been working for 10 years in JS, for 3 years in CampToCamp, and for 3 years on Nexus, which is a project I'm going to talk about. So Nexus, what is it? It's the next generation French system for managing alerts. When talking about alerts, I mean every call basically to the equivalent of 911, but in Europe, the European number being 112. So we are talking fires, attacks, or just broken ankle, anything really goes to the emergency system. And I'm going to be focusing more on how to respond to those calls, how to send the fastest vehicles and agents to those calls. So we're going to talk about routing. And why routing? Because what we need is to compute the cost in time between two locations, the location of the call, the alert, and the locations of the vehicles, agents that can go there and help the person who called. This needs to be performant because we are talking about sometimes life-saving calls. So we want to have a result in a few seconds. And this also needs to be performant because we will have heavy loads. We are talking about hundreds of calls per hour. So performance acts on both sides. And what we learned from the projects and from the community is that the number one factor to improve performance is to reduce the number of nodes in the road networks that we are dealing with. And what do we have to compute this time? We have real-time vehicles location. We have a static road network with length and speed, but it's dynamically changing based on operations, maintenance operation, like some roads can be closed, sometimes the speed limit will change. So this is about the data, and we have one tool we chose to use. There are many tools, but we chose to use PG routing. So we said that to be more performant, we need to have as less nodes as possible. And we have an issue with our dataset because most of the time our datasets will be too detailed. Here is an example. We have some nodes, we have some edges, and we can see that going from 1 to 4, we are taking 3 edges because those edges do not have the same attributes. The speed may vary, the costs may vary. That's a fact. The cost will always change because the edge is not the same length, is not the same speed. And sometimes we have other attributes. Here I put an example with name. It could change from one to the other. And some of those attributes may not interest us. When we are trying to compute the time it takes to go from 1 to 4, we don't care about the name. We only care about the speed. So what we want is one node less, keep the attributes that matters. The speed here is an attribute that matters, and remove the attributes that don't matter and merge the edges sharing the same attributes. We have a solution to deal with this issue. It's called contraction. Contraction, in its purest form, will remove any edge that do not bring any graph information. Here, going from 1 to 4 is the same as going from 1 to 2 to 4, and it was the same as going from 1 to 2 to 3 to 4. So in its purest form, the contraction would remove A, B, C, and only keep one edge from 1 to 4. This kind of contraction is part of the PG routing toolbox. It provides linear contraction. It's removing edges superfluous between nodes, and it also provides dead-end contraction. It's, well, the name is explicit enough. Our issue with this tool provided by PG routing, it's too aggressive. It doesn't take into account the attributes. And also, the result cannot be used as is. In some cases, you have to uncontract some of the edges that were contracted, and this part is counter-performant. So we decided that we needed to implement our, we looked around, didn't find any solutions that was good enough for us. So we decided to implement our own algorithm. We had some constraints. We wanted the algorithm to be fast, a matter of minutes, because the data may change often and we want to have the data as fresh as possible. We want to preserve the attributes. We want to preserve the topology. So going from 1 to 4 should still be able, we should still be able to go from 1 to 4 without any loss of information. We don't want any extra steps after the contraction. And we still want to remove as many nodes as possible because that's, well, that's what we want in the first place. Then we asked ourselves which technology to implement this algorithm. The fastest would have been C, C++. That's the language in which most plugins are implemented, but we didn't have any knowledge in this area. We tried with programming language, but it proved to be not as performant as we wanted. It would have been more precise, crawling from edge to edge and reducing from edge to edge, but it was taking too long. So in the end, we chose basic SQL, and it was more efficient because it's like bulk treatment. And also it was easier to maintain and easier to keep up with the project evolving. So now the algorithm, basically it's in 3 steps. It's all bulk steps. And we will see that PostGIS comes into place because it's part of the step are special due to the fact that we are in bulk mode. So the first step will be to identify the edges we want to contract. Then, as we are identifying all of them at once, we need to group those edges. We will group them spatially and by attributes, and then we will merge, and merging will be discriminatory too. So how do you identify the edges that you want to remove? You want to identify what we call linear nodes. Linear nodes are connecting only 2 edges. And here you can see it's easy to remove the middle nodes, and we only have 1 edge after that. And when it's not linear, you can see that removing this central node would not produce one line string, but a multi-line string, and it's not routable anymore. So we identify linear nodes. Then we identify edges touching those nodes, but it's not just touching. It has to be touching on both start and end. Why? Because if we took edges touching on only start on end, we would come across this kind of situation where here you can see we can't take all of these red edges and merge them together because we would also have a fork here. So we really need to have edges starting and ending on linear nodes. Then we will group those edges that we identified. We will group them by cluster. So this function, stCluster_dbScan, it's taking a data set and it's taking two properties. The first is the distance between the geometries that we want to group. And the second one is how many geometries you want to allow by group. So we decided to keep a distance of 0. Geometries must touch. And we decided that we would keep all the geometries at the end of the treatment. So we allow geometries to be alone in their cluster. And we run this once before we do the group by attributes, because it's taking some time to do, and we want, it's less precise than doing first the group by attributes, then the clustering. But the other way around, I tried it and it was taking, I stopped the process, it was taking too long. So after we have grouped by geometries, we will group by attributes. And we will see that this can lead to some inconsistencies, but we have another step to deal with these inconsistencies, which is merging. It's not used just for that. It's that we have grouped edges together and we want to transform those groups into a line string. When we get a line string, we are happy, we can use it. It's still, the geometry conforms to the previous edges geometry. It's still topologically correct. The end and start of this new edge will match the end and start of the previous edges. And we were able to keep the attributes. When we get a multi-line string after we merge the group, it means that something went wrong. We have several possibilities for the algorithm to go wrong. We will see that later on in the live example, but most of the time it will be clusters that happen because some lines were crossing. It's mainly because we are working with 2D data, and tunnel and bridges will cross when they are not crossing in real life, and we are not working with 3D data. Maybe at some point we should work with 3D data, but it's not the time. It's not the case yet. And also, we might have holes in groups because the group by attributes is done after the geometrical grouping, and sometimes the attributes will change along a line. We will see that also in the demo. In the real algorithm, we have some extra steps. We are cleaning the data before we process it, and we are still processing start and end edges. When I said we only deal with edges that start and end on linear nodes, we will add these start and end edges after the first run. And we also have a way to deal with combination of only 2 edges. So now I will do a quick demo of the algorithm. So I've prepared some data. I'm going to show the data was loaded in PostGIS, and I'm going to show it through QGIS, and it's OSM data in France. So here you see my QGIS. So this is data in France. This is Paris, actually. If some of you know Paris, maybe you will recognize the city. Well, it's a bit crowded, but when I zoom in, so these are all roads. And I've prepared some data of the steps of the algorithm. So first we identify candidate vertex. So those green points are all the edges that are connecting only two edges. So here we can see this point is connecting two edges, connecting two edges. So this will be the first step to identify then candidate edge. I will show you the difference between edges that could not be merged because they are when we keep start and end, we would have a multi-line string. So here is the example from the slides. If we keep all the edges touching those green dots, here we will have a fork. So we are only keeping the edges starting and ending. And then we are grouping geometrically. So here we can see that if I get the information on the clustered, we have a group ID here that was created and which will be the same along the line because they touch. So 27, 29, if I click the next one, it's still the same group. And if I go on another group which is not touching, it will change cluster ID. And then I will show you the result when the data is grouped by attribute. Visually, you won't make the difference here, but I have selected a few cases where we can see that the merging would go wrong. So I'm going to select on another screen. Yeah. So here is one case where the merging went wrong because you can see that those two lines are part of the same group that we want to merge. And well, you can see it's not possible. And the way it was grouped is because they are crossing the same lines. So this will be the most frequent case where merging is not possible because, as I said, we are working in 2D data and bridges and tunnels are crossing when they shouldn't. So we are clustering the wrong way here. But anyway, we decided not to merge those groups because they are not mergeable. And another case where we have issues, let me just select the other one. Is here, for example, we have a line. You can see that it's really one of our issues. It's one line and it's still split in many, many segments. So we want to merge those, but as we want to keep the attributes, we can see here that it's split because we are changing attributes. So I will select this one. So here you can see that what I selected is with the speed limitation of 80 km/h. And if I select the holes, they are changing speed limits. So this is one case where we can't merge and we don't want to merge because we would lose the attributes. So the main idea here is that we wanted to go fast for the treatment and for the algorithm conception, and decided that the final step, merging, would prevent anything from going wrong. So if I go back to my presentation, maybe I will leave still that. This was a short presentation of our work. I've wrote a blog post about it on Dev2. So here is the link, and I give more detail in this because, well, it's easier to give more details, not live. And so I took the time to to describe what were the issues, what we are talking about. I'll also describe completely the use case, the steps that we took, and I give the full code at the end. If you want to run that on your computer, you can. This code is based on here datasets, but it's almost the same with OSM data. If you want to run it with OSM data, you just have to use OSM2PO, which is a small executable that can load OSM data in a routable way. And then you will find the same attributes that I used, the speed, the class. It's really easy to go from one to the other. And one last thing I wanted to say is that with this algorithm, which is not complete, it was just really a first reflection. We were working on a network of around 500,000 edges, and we reduced the size by 18%, improving the performance by 24%. So it was really a good first step for us. And going further, well, we would like to evict as less candidate edge as possible. We are still working on this. And if we have the time, we would like to contribute in some way in the PG routing toolbox, because we thought it was really missing, that the only contraction available wouldn't take into account the attributes. As you, well, in real life, you always work with attributes. You don't only work with node and edges. So maybe at some time I will make a contribution in that way. And so that's all I wanted to share with you. Thanks for your attention.
Well, thank you very much for bringing that to us. I didn't really understand what contraction was before, and now I do. I've heard that the context I've heard the word contraction and routing into place before has always been contraction hierarchies. Does that ring any bells with you?
I didn't understand your question.
Have you played with contraction hierarchies at all?
I've not heard about hierarchy in contraction, but
okay, yeah, it's I think I'm looking forward to someone someday bringing a talk about it. It's a way of having basically multi-resolution networks and being able to hop between them, and be able to turn a.
You can have some tiles in road networks, but I wouldn't talk about contraction. And hierarchy would be a good term with tiles. It's what Valhalla does. They are splitting their network in tiles, and they are computing I don't know, routes between tiles, and then you only have to go from one point to the edge of your tile, and then from tile to tile. And so that's a lot faster.
Interesting.
Yeah, but we couldn't do that with PG routing, and we have other constraints that made PG routing the best choice for us.
Right. Cool. I had another question, but I forgot what it is. Tell me, how did you get into PostGIS? Personally? Yeah. What?
With my studies.
Yeah. Okay.
Yeah. I was interested in geographics, and it's like the basic tool in geographics.
That's really cool. And this was for emergency routing. So is this a live system now?
It went live this autumn. Yeah, and it's big stress because it's like emergency management. So yeah. So it's in production, and it's responding quite well. when I first did I chose the engine, because you have several engines. Page routing is PostGIS based, but you also have Valhalla and Grasshopper. Those are the main open source routing engines. And they are really great. And they are the other two, Grasshopper and Valhalla, are more performant, but they are less flexible. And we really need flexibility. So we decided to go with page routing.
Nice. I was kind of surprised that there's so many edges you could remove in the data. Like, why does the input data have so many redundant edges?
Oh, only talking about OSM data, it's split everywhere, because it's split on speed change, it's split on if you have a pedestrian crossing, it's split if you have like a sign. It's really precise, and the more precise, the more split. And we use only a few attributes on this data. Like if the pavement change, the edge change, or
Right. Was this so 500,000 edges? How much area does that cover?
oh, this is not OSM data, the 5,000.
Okay.
500,000. This is here. This is, I think it's TomTom. Well, it's a private producer, and this is the whole of France.
Oh, wow.
No. Sorry, it's not the whole of France. It's one department. So it's, I don't know, a tenth of France, maybe.
Laurie, there's a couple chat questions if you want to answer those, since you have a couple minutes left.
Yeah, but how do I see those? Because since I shared, I can't see Zoom anymore. Maybe I can stop sharing?
Yeah, that's fine.
Okay. Chat questions. You obtain a trip, a line string, but it's not usable to use. How do you do the commentary? Well, the contraction gives us a usable line, if that answers the last question.
I think the question is how to get back a set of street directions as opposed to a line. Like a human can't read a list of coordinates so well.
That's not the point of the project. We are not guiding the vehicles from A to B. We just want to compare costs, because that's a tool to help decision making. So we don't want to see that the vehicle we go along one road or the other. We just want to see that one ambulance, for example, will take 5 minutes and the other one 7 minutes. And then we will send the ambulance that takes 5 minutes. And for the question, does Valhalla use this? I don't think so, because they prepare their data. We were talking about tiles. So that's what they do. They don't really contract. They pre-compute tiles, and then when you are asking live for a route, you just have to go from your point to the edge of the tile, and then the routes between tiles is pre-computed.
All right, thank you so much for coming and sharing your experience with us, Laurie.
Thank you.